Welcome back, everyone. Well done for getting this far. We're now going to look at efficiency and thermodynamics, and this really does rely on, and again, if you're going into engineering or you're looking at engineering possibly as a course, you're definitely going to come across what we're going to talk about today. So I don't normally do our kind of learning objectives, but I think by the end you need to think about or be really clear on these points. So explaining what a reversible heat engine is, that's what we're going to do first. Then we're looking at the theoretical efficiency of our heat engines that we've been looking at over the last couple of lessons. And then the main reasons why an engine doesn't actually meet this theoretical efficiency. So first things first, we talked about an engine not being able to be 100% efficient because of these diagrams. All right, so we're looking at this heat engine. We know that in order for energy to flow from a high temperature source, we have to have a low temperature sink, which necessarily means there's energy that's going to be given over to that low temperature sink. All right, and that's the only way that we can achieve work done by my heat engine in the middle. We can also look at our indicator diagrams, so we can talk about this work. We know that we are going to lose this amount of work underneath because we have to put that much work in. So again, we can't be 100% efficient. But we're going to think about theoretically how efficient could it be. All right. And in terms of calculating the maximum theoretical efficiency, we need to think about the limit. So how efficient it could theoretically be. The thing that defines this, or the idea that defines this, is the idea of a reversible engine. Okay, and this is something that they ask quite frequently about during this topic. So the Carnot cycle, or the Carnot engine, is a reversible heat engine. The idea of a reversible engine is that the idea is that all of the heat, okay, so all of the heat that is transferred gets pushed into work that comes out of my engine. And I could do this in reverse. So I could take energy out of my low temperature sink and put work in, and all of that would be converted into heat energy that is dumped into my high temperature source. What we're saying here is that there is absolutely no loss of energy in the transfer between, so all of the heat energy that comes out of my high temperature source is turned into either work or goes into my low temperature sink. There's no losses to any other kind of system. Okay, there's no losses to atmosphere, there's no losses to friction, there's no losses to anything else. And if that's true, theoretically, we should be able to reverse that process. So I should be able to take that energy back out of my low temperature sink, okay, and put an exact amount of work in, and all of that work will be converted into temperature with absolutely no losses. All right, so that's what a reversible engine is. I can do it both ways. It causes maximum heat transfer from hot to cold. All right, so I can get heat out of a high temperature and put it into a low temperature with no losses. And I can also take temperature out of a low temperature sink and do work and put it into a high temperature source and have a perfect transmission of that heat energy. All right, if I look at this second cycle, it gives me the formula of the amount of energy going into my high temperature source is the work done plus the energy from my low temperature sink. All right, and that is a reversible heat engine. So it can go both ways, from hot to cold, and I can make it work from cold up into hot by putting work in. Now, if we look at the efficiency of one of these engines, okay, it depends on the temperature of the high temperature source and the temperature of the low temperature source. All right, we know that that is going to be the case. And we know also that the temperatures are going to be proportional, directly proportional to the amount of energy that is given to them. All right, that goes back to our kind of ideal gases, etc. Okay, so we can define the efficiency of an engine as the work done by the engine over the energy supplied to that engine. Okay, we're going to need both of these pieces of information. So one, that temperature and heat are kind of proportional. So my ratio of temperatures is going to be equal to the ratio of energies. And the second piece of key information, we can define the efficiency of an engine as the work done by the engine, this work coming out to the side, divided by the energy supplied to the engine. Now, in this example, our energy is being supplied by our hot source, and obviously in a reversible engine, the energy would be supplied from my cold source. Now, if we look at this diagram on my right-hand side, okay, we know that our efficiency is the work done divided by the energy supplied, which is going to give me work divided by hot, or the energy from my hot water source, or hot high temperature source. Okay, and the amount of work, again from my equation, I know that that amount of work is going to be QH minus QC. All right, so the work is going to be the difference between the amount of energy that is given by my high temperature sink and the amount of energy that's given to my low temperature sink. All right, so that's my work done, is the difference between those two. If I look at this in terms of so efficiency, this is a really useful formula. Okay, if I look at this in terms of kind of temperatures, all right, I know that my efficiency is this: QH minus QC over QH. Or I can separate that fraction out, and I can say QH over QH is minus QC over QH, and obviously QH over QH is 1. So that the efficiency is going to be 1 minus QC over QH. All right, so that kind of makes complete sense. My maximum efficiency is 1. I'm always going to have a negative value because I'm always going to have some heat energy given out to my heat sink. Now, for a reversible engine, we also have the ratio. So we kind of flip this equation. All right, it's exactly the same, but flipped over, because this time we're looking at the ratio of cold to hot in terms of heat energy and temperature. Now, I know that my efficiency, all right, is going to be 1 minus QC over QH. And I know that QC over QH is the ratio of TC over TH. So I can substitute that in, and I can go 1 minus TC over TH. All right, I can put those temperatures back together because that's TH and TH. And that gives me this final equation for maximum possible efficiency. So the maximum possible efficiency of any heat engine is TH minus TC over TH. All right, so really important formula there. Maximum possible efficiency, and we're talking about a Carnot efficiency, okay, named after the scientist who kind of came up with it. So my Carnot efficiency is TH minus TC over TH. We're looking at the temperatures of those two things. Now, this is a maximum possible efficiency. All right. In reality, engines actually have a lower efficiency than this. What I want you to do is pause the video and give yourself a couple of minutes of thinking about, why do you think that it has lower efficiency? What do you think are contributing factors? So pause it now and give that a go, and then play it again to kind of go through some answers. Okay, so hopefully you've had a go yourselves. And if you go reasons for lower efficiencies, let's have a look. So frictional losses. We've got moving parts of an engine. We're going to necessarily have some friction in there. So we're going to lose some energy during that process. It is usually taken in over a range of temperatures. So there's not an absolutely fixed hot temperature. All right. Okay, we're going to have a range of temperatures. That's going to fluctuate somewhat, and therefore that's going to affect my maximum possible efficiency. And the same for TC. It's not going to be a fixed cold temperature. All right, it's going to be rejected. There's going to be points where there's more energy or less energy being delivered in reality because of these frictional losses. We also have where we have flow inside of it. So where we've got air coming in and fuel coming in, there's going to be some kind of turbulence. All right, so there's going to be turbulence of all of those gases, etc., moving. Obviously, if there's turbulence, that means we've got particles physically moving, and that requires kinetic energy. So that energy has to come from somewhere. So the turbulence costs us, and it acts a bit like friction within fluids. And then finally, heat's usually lost to the surroundings and not just to the sink. Well, in this case, we're looking at losing heat energy to the engine block itself, to the cylinder itself. Those are going to heat up, It's not all going to be ejected out into the atmosphere. Okay, our cold temperature sink. Actually, what we're going to end up with is some of that energy going into the cylinders and the piston itself. All right, and what you'll find, and this is with particularly high performance cars, they're very well manufactured. You have to warm the pistons and cylinders up first because they expand and change shape. So you have to be very, very careful about what temperature you start that engine at, because they are designed to function at certain temperatures. If you start it from cold without heating it up or without going through the process that the car needs, you could actually damage your engine because they will be the wrong shape. They won't necessarily fit each other perfectly. So let's look at what this looks like in practice. Okay, if we're going back to this steam model that we kind of came across earlier. If I got to maximum efficiency, it's TH minus TC over TH. Okay, and remember that all of these temperatures have to be in Kelvin. All right, so if you're still not confident with Kelvins, you need to go back and make sure that you are. Theoretically, if we set the cold sink at 0 degree Kelvin, absolute zero, then we could have a heat engine that was perfect. But that's completely unachievable. So we're not going to be able to do that. You'd also use so much energy getting down to that temperature, you wouldn't have a perfectly efficient process. Okay, so we've got to be aware of that. But let's look at this equation. How can we make systems more efficient? Well, the bigger the difference is between TH and TC, the greater my efficiency is going to be. Okay, because the bigger that numerator of my fraction is going to be as a percentage of TH. So the bigger the difference between those two, the better. Okay, so we want a nice big difference between those two. If we look at our steam power station, steam coming from the boiler, about 400 degrees. Okay, for 400 degrees steam, goes through, and the cold reservoir down at the bottom, after the condenser, the water that sits down there is kept at about 10 degrees. So again, we've got about 390 degrees, either degrees Celsius or Kelvin. The differences are the same. By doing that, we have a very, very wide gap, and therefore we can use that to work out the efficiency. Now, as a kind of example for you, let's think about this in terms of a water wheel. Okay, so you might be being confused by the hot and the cold areas. Well, let's imagine that the top of my river is a hot sink, okay, which has got lots of energy, in which case this would be gravitational potential energy rather than heat. And obviously down at the bottom, my river has got a low gravitational potential energy. And as it comes over, it's going to fall and get through to the bottom. My engine, okay, if I put my engine halfway up the waterfall, my efficiency is only ever going to be 50%, because I'm only ever going to be able to harness 50% of that energy, because it's still got the rest of that gravitational potential energy to come down and talk about, all right, or get down to. I want the greatest difference between those two. So I want to put my water wheel at the bottom to create the biggest difference between the high energy particles and the low energy particles. All right. And to be able to do that, if my operating temperature, my sink temperature, was half of the source temperature, then the greatest efficiency I could hope for would be 50%. All right. If you look at this water wheel as the difference between the hot and the cold sink, all right, in terms of our equation. So I want that water wheel to be as big as possible, as big a difference as possible in between those two ideas. Now, practically, I know that I want the biggest difference between high temperature source and my low temperature sink. That makes complete sense. We know that. But let's think about the limitations. How hot can I actually make my high temperature source? What's going to limit me as a factor? Well, I can't make TH too high, because otherwise parts of my engine are going to start to melt. Okay, so parts of my system are actually going to start melting. Number two, my cold temperature sink is normally going to be the atmosphere. Okay, so atmospheric pressure is fairly consistent, so normal range. If I want to create a much colder environment, I'm going to have to put energy in. Okay, we've kind of got that idea. So therefore I'm decreasing efficiency. So normally our cold temperature sink is almost fixed at atmospheric temperatures. All right, so we've got a bit of a limit there, unless we want to start using some energy to cool it down, but therefore I'm going to affect efficiency. If we look at the cycle engine, we can help improve efficiency. All right, so where we've got different valves and ports, so our inlet valve and our exhaust valve that we saw opening and closing to allow that to happen, we want to very carefully design them to allow the air and fuel mixtures in and out with the minimum resistance. Okay, going back to that idea of turbulence, the easier that we make it for the gas to come in and out, the better that our system is going to work, and the less energy we're going to lose to resistance. All right, and if we lose less to resistance, we then get more efficient engines. The next one, friction can't be eliminated. All right, we know that if there are moving surfaces against each other, there's always going to be some friction, but what we can do is lubricate those surfaces. Okay, so if we have bearings, if we have different materials moving against each other, one, we can efficiently design bearings, make sure they're suitable, and two, we can provide lubricant for that kind of process. There's also, and if you go into engineering, you'll get used to this term, the idea of viscous drag. Okay, the oils themselves have viscous drag, so physically moving, there's a kind of internal resistance of those materials. Now, that's the kind of idea of efficiency, and there's one more little bit that you need to know about for this topic. In reality, most power plants are less than 35% efficient. That means that we waste 2/3 of that energy. Okay, if you think about it in a different way, all right, essentially your engine is actually better at heating the environment around it than producing a certain amount of work. Okay, so if you look at heating, it's heating the atmosphere, but you're producing much less work. If we look at how we can increase the efficiency of power plants, we can use this idea, and you need to understand this term CHP. So we've got combined heat and power. Now, this is a simple idea. At the moment, if we boot out 2/3 of our energy as wasted heat into the cold sink, it's just wasted, it's gone. In order to improve efficiency, what we can do is use that thermal energy that goes out to my cold temperature sink as thermal energy to provide heat to local industry or buildings. Okay, so instead of it being wasted and just ejected into my atmosphere, what I can do is then find a use for that waste energy. So I can't stop it being produced, but what I can do is start using that energy. And if I'm using it rather than wasting it, then the efficiency of my whole system goes up. All right, so it's a bit of a different idea. It's kind of repurposing that waste material and making it useful to us. This is done worldwide, and the whole idea is using that waste energy. Is normally used for heating houses, factories, business units. Greenhouses are a good one because we have to keep them nice and warm. Okay, so if you've got industrial greenhouses where we're growing stuff, we can use that energy, and it's really kind of good for those plants. It hasn't really taken off in Britain, okay, because most of our power stations are sited away from centres of population. We don't want them in the middle of towns. All right, so we actually put them away from large scale population, which makes using this heat energy very difficult, because if I've got to transport it, transporting that energy isn't easy. In other countries, they have a different kind of setup, and they're often those power stations are closer to civilization or to industry in order to make the most use of this. Now, if instead of looking at industrial power stations, if we have smaller electrical generation schemes, so if we have smaller scale operations using heat engines, all right, whether that be just for a local town in the countryside or for a village in Scotland, something like that, if we set that up near where people live and work, what we can do is use that waste heat energy for local heating, etc. All right, and therefore we're not wasting that energy. we gain more of that useful energy per kilogram of fuel. Okay, we're getting more out and using it for actually beneficial purposes. The kind of sectors that really benefit, okay, are hospitals, schools, chemical, brewing and paper industries, because these require us to generate quite a lot of heat to make the reactions happen. Okay, and hospitals and schools, obviously, they do require a lot of energy. Okay, especially for heating a large building such as a hospital or school, it costs a lot of money. So if we can repurpose some of this thermal energy that we're going to create anyway, that improves our efficiency. So let's go back to this final idea. You should hopefully know what a reversible heat engine is. You can discuss how efficient it can be in terms of the Carnot cycle, and you have to know that equation. State the main equation or main reasons why engines can't achieve it. And finally, you just need to have an understanding of what a CHP system is, so a combined heat and power system. If you now go over, you can answer those questions on efficiency in the thermodynamics questions and answers pack. Good luck, and I'll see you next time for the final video.